Hello friends, welcome to our next session. In this session we're going to look at analysis of variance with the acronyms ANOVA. Analysis of variance is simply a statistical tool which is used to compare two or more means. So we're going to look at ANOVA 1 and ANOVA 2. Now this is one of the topics that most students find a challenge. I'll try as much as possible to simplify it. To start with, ANOVA is part of hypothesis testing, which follows the 5 steps that are involved in hypothesis testing. These include, number 1, testing the hypothesis. The null hypothesis, which is denoted by HO, is given by mu1 is equal to mu2 is equal to mu3 is equal to mu n, depending on the number of means that you are dealing with. Remember, ANOVA is only used when you are dealing with variations in means starting from 3 and above. The alternative hypothesis here will note to say at least one mean is different. Our second step in hypothesis testing is in stating our level of significance. So the level of significance will be 5%, with 0.1, and the ANOVA table uses what we call the F distribution table. I'll take you through how to read the F distribution table closely. The third step is that of rejecting our F calculated based on the statistical reading. Then we go to calculating our F calculated and making a conclusion and a decision based on the readings. Today, I'm basically going to take you through how to set up an ANOVA table in the simplest possible manner. But we need to go through the dictionary. How and what the terms SSTRT stand for. This is simply the sum of square treatment, sum of square total, sum of square error, sum of square block. The DF stands for the degree of freedom and the N stands for the number of blocks. The capital N, however, stands for the total elements in the sample space. So we have what we call a two-way ANOVA and a one-way ANOVA. A two-way ANOVA has variations coming from two sides, from the treatment and from the blocks. So in layman's language, the treatments are simply columns and the rows are simply the blocks. So from this arrangement, we can tell that our K, which stands for the number of treatments, is equal to 4. And our blocks, which are the rows, are 3. The N is simply the total number of the elements that we have here. So how many elements do we have? We have our 12 elements in the first table. In here, for the two-way ANOVA, you must take note that the number of columns and the number of rows must be regular. For a one-way ANOVA, it's not always a must that they will be regular. What do I mean by regular? You may have 4 elements in the first treatment, 4 elements in the second treatment, and 4 elements in the third treatment. For a one-way ANOVA, that is fine. However, you could still have an irregular number of n sample spaces. So we have 2, we have 4, and we have 3 in A, B, and C respectively. Now this now takes me to how we erect an ANOVA table. So I want you to take note of the form that we use when erecting the ANOVA table. So I'll start with the one-way ANOVA table. So we have what we call the source of variation. The sources of variation are the treatment, we have the error, and the total. So using the key that we're using there, SS stands for the sum of square. So the figure that will be here is called the sum of square treatment. And what we're going to have here is sum of square error. and this is called our sum of square total. So the sum of square treatment using the formula is simply given by the sum of each treatment squared minus a correction term over capital N. We have what we call the sum of square total, which is given by summation of x squared minus the correction term, which is summation of x to the power 2 over n. And our error is simply the difference between the sum of square total minus the sum of square treatment. Then we go to what is called the degree of freedom. Our degree of freedom for the treatment is simply k minus 1. The degree of freedom for the error is simply n minus k. And the degree of freedom for the total is capital N minus 1. We also have what we call the mean of squares. To find the mean of squares, we simply divide the degree of freedom into the sum of square. So this is called our mean square treatment. This is called our mean square error. I repeat, how do we find the mean of squares? So the mean square treatment is simply the sum of square treatment over k minus 1. The mean square error is simply the sum of square error over its degree of freedom, which is n minus k. Then finally, we get to calculating our f calculated, which is simply the mean square treatment over the mean square error. This is what we call the f calculated. So this is how a one-way ANOVA table is constructed. I'll take you through the format for a two-way ANOVA table. So it's very important as students that you're able to memorize or perhaps understand how the one-way and the two-way ANOVA table is done. So the difference in a layman's language is this. A one-way ANOVA only has treatments, and the two-way ANOVA has both the treatments and the blocks. So we're going to have the same format where we have SS, which is the sum of squares, so our sources of variation here, we have the treatment, the block, the error, and the total. Wherever you are, I want you to keep trying how to fuse in the formulas we've been discussing. So let's start. The sum of square treatment, what are the acronyms we use? SS treatment. The sum of square block, what do we use? SS block. And the sum of square error, SS error. Then we have the sum of square total here. So the degree of freedom for the treatment in a two-way ANOVA is simply k minus 1. The degree of freedom for the block is n minus 1. And interesting enough, the error is simply the product of the two. So it will be k minus 1, n minus 1. That is how we find the degree of freedom for the error under a two-way ANOVA. The degree of freedom for the total is the same, which is capital N minus 1. So when we divide the degree of freedom for the treatment into the sum of square for the treatment, what we get is called our mean square treatment. This is our mean square block, and this is our mean square error. So we're dividing the mean square error into each of them to get the F calculated for the treatment. As well, to find the F calculated for the block, we simply divide the mean square block over the mean square error. Now, good to go. So now that I've given you the format that we use in this segment of our session, I just want you to understand that this is one of the simplest topics in